The baseline command rhythm of the 20th century relied on physical mechanics and human deliberation. Planners gathered intelligence over days, held manual briefings, and transmitted orders over discrete, analog channels. Because intelligence gathering was slow, military staffs operated within strict legacy planning windows. An operation was often mapped out over months, its pace dictated entirely by the predictable physical mobility limits of past units. Earlier logistics structures were completely siloed. A planning phase concluded, triggering a static logistics push, allowing for physical mobility. But rapid technology cycles immediately fracture this rigid format. The moment new operational data arrives, a static plan becomes completely obsolete. A sequential planning structure collapses when subjected to continuous data velocity. An analog process simply cannot process incoming intelligence fast enough to adjust a rigid logistical chain in real time. Modern defense planners operate under intense global security pressure. Shifting regional posture trends require military forces to maintain constant readiness across wider, more dispersed geographic areas. Two opposing forces compress modern force posture. Skyrocketing life cycle economics make platforms harder to field, while rapid technology cycles make older platforms instantly vulnerable. Global alliances are shifting to distribute the load of supply chain strain and match procurement rhythms required for modern equipment. The current force demands placed on these modern units no longer allow for the downtime inherent in earlier deployment cycles. Equipment and personnel are required to be continuously active. To maintain operational readiness, force planning must abandon static windows entirely. Survival requires adopting a continuous, systemic process of observation, calculation, and immediate action. The architecture of this continuous system is dictated by the bedrock economic constraints of present defense manufacturing. This split screen tracks the economics of modern platforms. Primary manufacturing cost drivers trace a steep exponential curve, while maintenance inflation compounds mathematically. Contract delays and systemic slowdowns in spare parts create cascading operational risk, grounding expensive hardware over a single component. This extreme lifecycle stress on equipment inherently restricts physical force availability. Commanders have fewer operational assets at their disposal at any given moment. While physical platforms are scarce, the opposing technological constraint provides the exact opposite problem: an overwhelming infinite volume of incoming digital inputs from modern battlespace networks. A network graph maps the operational influx of data. Information pours in simultaneously from autonomous drone formations, sensor networks, and electronic attack systems. These attack systems are specialized platforms designed to disrupt, deny, or degrade an adversary's use of the electromagnetic spectrum. This creates an inverse operational relationship. As digital data velocity increases, the economic tolerance for hardware loss steeply decreases. The gap between hyper-fast digital inputs and slow, economically fragile hardware creates a structural vulnerability. Managing it requires an entirely new command rhythm. The limiting factor is the human brain. Personnel handling high data volumes face cataclysmic cognitive pressure as raw intelligence floods the command center. Leadership stress points and combat fatigue correlate directly to the volume of unfiltered sensor data. A human operator cannot manually process thousands of competing data points to find a single critical threat. Tempo 2040 solves this by replacing long planning windows with ultra-short planning cycles. These cycles are fed by constant observational input rather than static reports. This flowchart models intercepting raw data. The chaotic stream passes through structured decision gates. Algorithms establish strict trust boundaries, weighing statistical probabilities to recommend specific courses of action. This actively strips away false signals, passing only validated, prioritized alerts to the commander. By forcing real-time assumption checks at the machine level, the system protects the cognitive capacity of commanders, allowing them to handle immense uncertainty without being paralyzed by noise. Algorithmic data validation and strict trust boundaries are mandatory prerequisites. Without them, human decision-making in the Tempo 2040 framework is mathematically impossible. Once the internal command center filters the data, the focus shifts outward to the execution of multi-domain operations. This topographical map visualizes massive, overlapping operational zones. The battle space splits into multi-layered digital maps spanning land, air, naval, cyber, and space domains. A pulse in the upper space or cyber layers directly dictates timing, instantly triggering a physical reaction in the land and naval layers. Ground movement is no longer isolated. It must be perfectly synchronized with real-time sensor fusion flows. Sensor fusion flows are continuous streams of data combined from multiple distinct observational nodes to create a single, accurate operational picture. To survive coordinated electronic attacks, physical forces require immediate air support alignment and continuous naval repositioning, executed the moment the sensor network detects a threat. When facing incoming drone strike sequences, units rely on fast relocation sequences, shifting their physical footprint in perfect unison based on algorithmic targeting warnings. Multi-domain operations cannot be sequenced manually. Inter-domain algorithmic timing is a mathematical requirement for physical survival on the modern battlefield. However, decision speed and algorithmic timing are entirely void without modern logistics flows to sustain the physical hardware. Legacy operations relied on a blind push of supplies to the front. The modern framework relies on continuous, real-time load tracking to deliver exact quantities precisely when needed. This logistical network map illustrates fuel flow forecasting and algorithmic ammunition timing. Supplies move dynamically toward forward operational nodes. When a transport route is disrupted, the system performs instantaneous recalculation, mapping fallback sourcing to keep supply lines intact without manual intervention. The system actively maps spare part risk across the network to ensure naval and air readiness, calculating the exact moment a replacement component will be required before a breakdown occurs. Because these supply routes are vital, they require strict intelligence protocols. Planners implement low-visibility protocols to protect them. Low-visibility protocols are strict operational procedures designed to minimize a unit's electromagnetic and thermal signature to avoid detection by enemy sensors. Logistics has evolved from a trailing support function into a predictive constraint. It entirely dictates the pace and scale of frontline operations. To evaluate the total health of the integrated Tempo 2040 system, commanders rely on quantitative readiness metrics rather than visual inspections. This systemic dashboard tracks core performance metrics, response time, decision accuracy, and logistics stability. The system is interconnected, creating specific fragilities. If the communication fault rate spikes, personnel condition deteriorates without clear data, and response time dynamically drops. To correct these faults, the system utilizes a digital after-action review loop. Precise data capture allows planners to run accurate timeline rebuilds of every engagement. Cross-unit assessments and fault tracking actively refine the predictive AI models, ensuring the logistics algorithms and trust boundaries are sharper for the next deployment. True readiness is no longer measured by a massive stockpile of static physical assets. It is the stabilized mathematical output of a self-correcting logistical and command system. Operationalizing this framework requires rigorous macroeconomic policy and deliberate force planning at the government level. Long-term procurement and manpower balance must align directly with rapid technical cycles. Buying hardware that cannot integrate into a real-time data flow is a waste of capital. Partner cooperation and alliances are essential to distribute the extreme cost outlook and mitigate widespread supply chain risk across multiple industrial bases. The final Tempo 2040 model is a unified, updated phase chain. It bridges precise logistics flows directly with modern algorithmic command processes in a continuous loop. The defense force of 2040 is an integrated, continuous digital ecosystem. Strategic policy must treat it as a single organism rather than a collection of static platforms to maintain absolute operational readiness.